Tantor Audio, a division of recorded books, presents The Shortest History of Our Universe, The Unlikely Journey from the Big Bang to Us, by David Baker. Foreword by John Green. Narrated by Keval Shah. Foreword by John Green. Humans like a good story, and since we are, as a species, somewhat narcissistic, we're especially fond of the story of ourselves, how we came to be here, and why. These days, we call that story history. But for too long, we've had a narrow definition of history, one that dramatically distorts reality. As a high school student, I was taught that recorded history began about 5,000 years ago, with the invention of writing. However, that definition leaves out almost all of the human story, at least 95% of it. Of course, we cannot know the humans of 100,000 years ago as intimately as we know Genghis Khan or Cleopatra, but omitting them from the story makes the human story seem much newer than it actually is. When you imagine that our story begins with the emergence of agriculture or writing, or any particular innovation, the human story seems to look like an ascending line. Lives get longer, people grow less hungry and less poor and more educated. Technological improvements are shared more widely, and innovations pile upon innovations to ensure that life inevitably improves. For most of human history, that wasn't really the story. Important innovations were made, as small communities passed down knowledge from one generation to the next. But human lives have not always grown consistently healthier or more productive. As you will learn in this book, we nearly went extinct long before we figured out how to develop agriculture, or steam engines, or antibiotics. We have been the dominant species on this planet for the briefest flicker of our history. And until we understand that, we cannot reckon meaningfully with the dramatic and sudden changes we're making to our planet and its biosphere. Narrow views of history also too often create a false dichotomy between the hard sciences, chemistry, physics, biology, and the soft humanities, history and literature, and anthropology. Human stories cannot be viewed in isolation. We can't understand 14th century Europe without learning about the biology of Yersinia pestis and the rats that carried it. And we can't understand how life came to be on Earth without glimpsing how time began in the first place, and how each of us is made from stars. In The Shortest History of Our Universe, David Baker introduces us not only to the history of our species and our planet, but also to the history of our vast universe. We are not the end of that story, nor its beginning. Instead, we have emerged in the middle of a tale that will continue long after we are gone. Glimpsing the breadth of the universe's history can make a person, or a species, feel very small indeed. And yet, it is also a reminder of how wondrous life is, and how astonishing. As Baker writes, when we look into the night sky, we are not looking at the universe. We are the universe looking at itself. Introduction. This book follows the continuum of historical change of all the stuff in the cosmos, from the Big Bang to the evolution of life to human history. As simple clumps of hydrogen gas are transformed into complex human societies. History allows us to live many lives instead of just one. And this particular story instills in us the combined experience of billions of years. Much confusion over human identity, our philosophies, and our future could be resolved if only the average person knew the key beats of the story of everything, at least as well as they knew the key moments of their national histories. Zooming out to take a bird's eye view of 13.8 billion years allows us to see beyond the chaos of human affairs to the overall shape and trajectory of history. The thread that runs through the entire grand narrative is the rise of complexity in the cosmos. From the first atoms to the first life to humans and the things we have made. It allows us to traverse aeons without drowning in detail, because the amount of detail an answer requires depends on the nature of the question. In this book, we ask simply, where did we come from? And where are we going? Regarding the future, I am speaking in terms of the next 100 years, the next 1,000, the next million, the next billion, and even the next trillion to quadrillion to the potential end of the universe. The shortest history of our universe explores all that too. For the science phobic, rest assured there will be no math equations, and foreign cosmic phenomena will be boiled down to plain speech. For the history buff, humans may occupy only what a colleague called the thinnest chip of paint at the top of the Eiffel Tower of 13.8 billion years, but for very real, objective reasons, humans occupy a very important role in the story. As far as we know, human societies and technologies are thus far the most complex structures in the entire universe. We are a tightly woven web of 8 billion whirling brains, each with more nodes and connections than there are stars in the Milky Way. The next rise of complexity is likely to come from us, or at least something like us, that evolved elsewhere in the cosmos. French historian Fernand Braudel once likened the political events of recent history to bubbles and swirling foam atop an ocean of deep time. Here today, gone tomorrow. To truly understand where we are and where we are going, we must look below to the deeper currents and tides. The tendency of complexity to increase in the universe moves the entire historical ocean. This trend toward rising complexity created us and continues to change us. Astoundingly, a self-aware humanity currently has the power to control where complexity goes next. Our past can be divided into 3 phases. The inanimate phase, 13.8 billion to 3.8 billion years ago. The animate phase, 3.8 billion to 315,000 years ago. The cultural phase, 315,000 years ago to the present. Each phase corresponds to a major increase in complexity. The inanimate phase covers the non-living cosmos, from the Big Bang to the formation of the Earth. The animate phase starts with the first microscopic life at the bottom of Earth's oceans, and sees the evolution of billions of complex species and ecosystems. The cultural phase begins with the ability of humans to accumulate more knowledge and develop tools and technologies over a short period of time, drastically changing how we behave and live, despite the fact our biology has not changed much. In each phase, complexity drastically increases, from the grinding crash and thunder of the cosmos to generations of evolution by natural selection, to cultural evolution or collective learning. The pace of historical change also accelerates rapidly. Cosmic changes can take billions of years, and evolutionary changes millions of years, whereas cultural changes are measured in millennia, centuries, years, even days. Every shift in complexity, each major event of the past, every newly emerged form of evolution builds on what came before it. Our story also has a fourth phase, the unknown, in which complexity will leap forward yet again and set off an entirely new stage of cosmic evolution and historical change. Perhaps humans will give way to the accelerated creation and innovation powers of self-aware AI, artificial intelligence. Perhaps humans will upload their consciousness to computers and travel across the galaxy. Perhaps quantum physics will allow unprecedented manipulation of the building blocks and fundamental laws of the universe. All we know for certain is that unless complexity is outright destroyed, some sort of increase in complexity is only a matter of time. And in the human realm, the changes keep coming faster and faster. The generations of humans alive today occupy a pivotal role in a story that has been unfolding for 13.8 billion years. By understanding the long-term story from billions of years ago, we are better placed to make long-term plans billions of years into the future. Part 1. The Inanimate Phase, 13.8 to 3.8 billion years ago. Chapter 1. The Big Bang. Wherein all the stuff in the universe appears, space appears to give us somewhere to put all that stuff. Time appears and makes it possible for that stuff to change form, i.e., have a history. All that stuff is primordial energy and matter that transforms into the diverse range of things around us. Bang. About 13.8 billion years ago, a tiny, hot, white speck appeared. It was so small that at first it could not be seen by the naked eye, or anything except the most powerful of modern microscopes, had they existed. This was the appearance of the space-time continuum, and the extremely hot, densely packed energy within it. Nothing existed outside of it. All the ingredients for everything in the universe were within it. They have simply changed form since then, as if the universe were a ball of clay, shaped and reshaped into myriad forms over billions of years. The absolute first date in all of history is 10 to the power of minus 43 seconds after the Big Bang, or 1.0, with the decimal place moved to the left 43 times. A tiny sliver of a second. It is the smallest possible chunk of time that we can measure. A smaller fraction of time would be physically meaningless, because nothing in the universe can move fast enough to show that even the slightest change has happened in a smaller amount of time. 10 to the power minus 43 seconds is the amount of time it takes for light to travel the smallest amount of distance at the quantum level. Any smaller snapshot of time, for instance 10 to the power of minus 50 seconds, looks exactly the same as 10 to the power of minus 43 seconds. It is like the first frame of a film. The universe was smaller than an atom, or even one of the particles that make up that atom. Because of the pressure of everything in the universe being contained within that small space, it was incredibly hot, up to 142 nonillion Kelvin, or 142 followed by 30 zeros. So hot, it is practically the same in both Celsius and Fahrenheit. The laws of physics themselves could not stay coherent. The universe was so hot that the very laws that make it work were in melted form. It was true, unadulterated chaos. Alice in Wonderland, and a pint of LSD. A tiny fragment of a second later, by 10 to the power minus 35 seconds after the Big Bang, the universe had expanded to the size of a grapefruit. It would have become visible to the naked eye. It cooled below 11.3 octillion Kelvin. This was cool enough for the first four fundamental forces of physics to harden into their current form: gravity, electromagnetism, and the strong and weak nuclear forces became coherent. We were now a universe governed by physical laws. If they had hardened into a slightly different balance, the universe would have evolved completely differently. During this time, a ripple at the quantum level made tiny pinpricks of energy clumped together. Energy in the universe was just ever so slightly unequally distributed. These clumps of energy would evolve into all the matter, complexity, stars, planets, animals, and stuff in the universe, including you. By 10 to the power of minus 32 seconds after the Big Bang, the universe was about 3 feet, or 1 meter, wide. And the heavy lifting was over. The clock was wound, its mechanisms were set in motion, and it began to tick. In the first split second, our destiny was already etched into the very fabric of the cosmos. And the rest, as they say, is history. For the next 10 seconds, the universe grew to 10 light-years wide, swirling with tiny particles that had congealed from pure energy as the universe continued to cool to 5 billion Kelvin. There were quarks and antiquarks, positrons and electrons, the opposites of each other. Matter and antimatter. Much of the matter bumped into the antimatter and exploded in a flash, turning back into energy. Only 1/1000th of the matter could not find an antimatter partner, and it is only this tiny fraction of matter that forms all the stuff in the universe we see today. Here, within the first 10 seconds of the story, is a miracle that saved us from non-existence. Over the next 3 minutes, the universe continued to expand. It was over 1,000 light-years wide, a sea dominated by thick, merciless radiation. The surviving quarks were forged together by the still intense heat into protons and neutrons. These protons and neutrons were in turn forged into the core of hydrogen and helium atoms, the nucleus. Hydrogen and helium were the simplest and first of all the elements to exist. Hydrogen requires only a single proton in its nucleus. Helium requires more ingredients and was therefore in the minority. The universe cooled below 100 million Kelvin, too quickly for many of the other elements to be created. Only trace amounts of lithium and beryllium. Heavier elements would have to wait for the creation of stars many millions of years later. The universe continued to expand and cool for thousands of years, longer than Homo sapiens has existed. By 380,000 years after the Big Bang, the universe was over 10 million light-years wide, and it had cooled to 3,000 Kelvin, twice as hot as lava, and enough to melt gold or cause a diamond to drip like an ice cube on a summer's day. The heat was still enough to obliterate most complexity, but it was cool enough for hydrogen and helium nuclei to capture electrons and become full-fledged atoms. The universe began to fill with clouds of gas. The universe had also become less dense, allowing photons of light to travel freely through the thick soup of radiation and particles for the first time. There was a blinding flash of light as these photons headed in every conceivable direction. This flash of light is known as the cosmic microwave background, CMB, and can be detected in every direction in the universe today. In fact, if you set your radio or television to collect only static, about 1% of that static will be from the CMB. It is the first baby picture of the universe, and the first visible artifact of our deep past. How do we know the Big Bang happened? We know the Big Bang happened for several reasons. For starters, we can't find anything in the universe, either on Earth or through a telescope, that is confirmed to be older than 13.8 billion years old, which is the current estimated age of the universe. If the universe was infinite and eternal, we'd be tripping over stuff that was 105 billion, or 802 trillion years old. Second, the fact that normal matter in our universe is mostly hydrogen and helium is exactly what you'd expect to see if the expanding universe was super hot for a few brief minutes, but then cooled down quickly, without time for many heavier elements to form. Again, if the universe was infinitely old and infinitely big, we'd have no clear explanation why the chemical composition of the universe is the way it is. In an infinite universe with an eternity of stars blowing up in supernovas, there would be no clear reason not to expect just as much gold to exist in the universe as hydrogen. Third, in the 1920s, Edwin Hubble was mapping the cosmos and discovered that most galaxies are heading away from us as space expands. Logically extrapolating from that and calculating backward, Hubble figured out that all the galaxies in the universe must have been smooshed together at a single, fixed point. Despite this discovery, the Big Bang theory was not the dominant theory of cosmology for decades. Which leads us to the fourth and most crucial piece of evidence: the cosmic microwave background that emerged 380,000 years after the Big Bang. If the Big Bang theory were true, then after a few thousand years of the universe expanding, the crush of matter and plasma and radiation would be spread out enough for light to be able to travel freely, and there would be a brilliant flash across the cosmos. In the 1940s, physicists predicted we should be able to see the remnants of this flash everywhere in the sky. This is precisely what was discovered in 1964 by two radio engineers, Arno Penzias and Robert Wilson, who weren't even looking for it. They were trying to eliminate all the static on a highly sensitive radio antenna, but they couldn't get rid of a small hiss. And after many calibrations, and having shot the pigeons that shat on the antenna, a physicist from Princeton told them what they had found. From that point on, the Big Bang became the dominant explanation for the start of the universe, and all the work that has happened since has only confirmed or clarified the general framework of this theory. What does the universe look like? In the first split second after the Big Bang, the universe inflated from the size of a quantum particle to that of a grapefruit. Within a second, it was larger than our solar system. 4 years later, it was bigger than the Milky Way. The universe as we know it is currently 93 billion light-years across, which means there are stars and galaxies that were born billions of years ago that are so far away their light hasn't had a chance to reach us, since only 13.8 billion years have elapsed since the start of the universe. The stuff we can see looking out from Earth is called the observable universe, but there are a lot of things beyond that horizon that we cannot see. Moreover, because light takes time to travel from a distant object, the further away we look, the further we are looking into the past. For instance, a neighboring galaxy, Andromeda, is 2 million light-years away. So when you look at it through a telescope, you are seeing it as it existed roughly when Homo erectus started roaming the Earth, and saber-toothed tigers were still a cause for concern. The observable universe can be seen looking in any direction from Earth. In that sense, the observable universe is a sphere. However, that is not the shape of the entire universe. Physicists have determined that the universe has zero curvature, which means it does not bend back on itself at some point. It stretches on and on, like a tabletop in any direction, constantly expanding for all eternity. The observable universe is just one patch on it, like the ring left by a coffee cup on a table. And Earth is just one tiny fibre of wood lodged somewhere inside that coffee ring. The colour of the universe is beige,
Sample complete. Ready to continue?